Professor, I think your microphone is not activated.
Yeah, actually it was like that. So let's go back to Keynote and share. It's kind of tricky. Now it should be okay. I hope. So let's restart. So one of the most requested things was to explain last assignment on Blackboard. And this is the base for today's review. Also getting some of your previous questions, right? So let's start point by point and start from the ground. We had two questions related to the ground. One is about the geological surveys, right? And actually, most of the class did okay, but still quite significant percentage went through the SPT. There is not mystery here. It is well explained in the lecture. You can go back and things are already commented. So there's not anything to think about, just to remember. There was excavation, right? And this was kind of tricky, kind of seemed too mysterious. This is what we did in class, right? And I think most of you remember this was kind of getting you some kind of sense of a common ground. And we said that 10-meter excavation would be 33 floors. I was surprised it was so difficult to make the thing we requested in Blackboard. I added a bit more complexity just to be a bit more realistic, because at home we have a bit more time, but it was like really 5 minutes exercise, right? So this is what we had, 28 meters. I had 5 correct replies. Of course, I did by hand, so I might have been wrong. I'm not worried about being wrong because if we have 50 people doing it, probably some people will find a mistake, right? But actually, I think it was mostly right. I will give you the solution. One thing with Blackboard, hopefully we will make the exam offline this time. Take your activity sheet, please. Hey. Yes. But Blackboard is not artificial intelligence at all. So to reply, you have to put just a 28. If you put 28 meters or approximately 28, Blackboard doesn't understand, right? So you have to go by hand, one by one. I have to correct your score. So officially it's just 2 correct, but actually 5 say 28. What was surprising is that the range of replies was between 5 and 242 meters. Which is telling what's going on, right? A few people were around 20, 28. So if we say it in class, 10 meters excavation is 33 floors, it makes sense, okay? Just a very rough approximation, 60 floors will be about 20 meters, right? But we have another thing, we have the foundation, which is very heavy. This is why I on purpose added that foundation element. And that's what complicated a little bit. So how we make the calculation? So the problem is understanding the problem and having it right? And this is where most people got confused. Because of going too simple and saying, okay, 36 floors is 10 meters, so 66 floors probably is 20 meters. And I had many 20 meters, right? But you have to balance on one side the building. Building is 60 floors, number of basements we don't know, and the weight of the slab. Right? This is the weight of the building. And then we have to put this in balance with excavation, which is H meters of excavation we don't know. And that's all. And you make the numbers. So we have the ground, we have the tower. We know this is 60 floor, right? There's not mystery. So this weight is well known, right? There's no problem here. We have the excavation, which is unknown h, right? And we have, this includes the foundation, which we know it's 2 meters, right? So the basement floor are h minus 2 meters, right? I think. You can correct me if I'm wrong. So the number of floors here will be h minus 2 divided by 4, right? Because we said one floor is 4 meters, right? Do you follow me so far? Okay, so the building weight, which is the part A, right, is 60 multiplied by 600, right? We have a 1 square meter to simplify, right? Plus h minus 2 divided by 4 by h. Am I right? No, this is not right. Right. This is 600, right? Plus 2 multiplied by 2,500, which is the weight of the foundation. This is side A. Side B is h multiplied by, we said 1600, right? So make A equal B, and then it's just a normal equation. This is probably elementary school level mathematics. So the mathematics are usually easy, basic. The problem is not really thinking on the problem, not making it, and making a diagram, making it graphic makes it very easy to solve, right? So actually, it was like a 28 point someone, and the basement was like a not exact number of floors, but that was not the point. The point was exercising and making sure you understand the basic problems, right? I will not do the mathematics. You can do for me and tell me if 28 more or less is correct or not. At least 5 more people agree with me, and I think it's the solution, and it makes sense, right? So that means those 2 meters of foundation have a huge impact on the weight of the building, right? That helps the stability, of course, but there is both a huge amount of material and a lot of weight. Any question here? Well, so always try to understand well the problem. This is not a question of being fast, right? This question of having things clear. To solve any problem, even if we do fast, our mind must be slow, right? Always. This was not a complicated problem, but most structural problems have to start in this way. You have to really understand the structure very clearly and work slowly without hurry to make sure you have all the factors. And then somebody will make the numbers, or the computer, right? That's secondary. Can we go next? Okay. So what happens with excavation? So usually by experience, we see an excavation and nothing happens, but that's not always the case. This is taken from a Japanese handbook. I have a lot of Japan because Japanese are very good at documenting everything, right? And we have the Hanji or Hanja, which are also helpful for Chinese students who are not familiar with English. So there are very common cases. One is what they call the boiling of the ground. If the ground is not rigid, it's plastic, the difference of friction of the weight of the floor may make it just protrude. And it's quite nasty to happen when people working there, right? So that means before making an excavation, you have to know very well the nature of the ground. And the engineers have to be clear about it. Otherwise, if we have water, especially with a flexible ground, is when you break the balance, the water will push. And this is very slow process. Of course, excavation goes along days or weeks, right? So very slow process, and the earth moves very slowly, but it may end pushing, and that may ruin your foundation or several floors you built already, right? So these things which really happen, and you have to be aware of it. And we know this because it is good to remember our dear Newton, right? The balance of force must be 0, right? And if there is one action, there will be a reactive force always, right? This is the most basic thing we do in structures. This is Newton. And this is what happens when you don't consider the ground. This is a town in Brazil, Santos. And actually, we had a few years ago an exchange student here, and he asked about this. And of course, they are worried, because if that continues, buildings may eventually collapse. So the question was, how will they collapse, right? Well, we don't know. Probably they will rotate and they will fall on themselves, which is the worst case. The question is having high rise, and this is for Korea, is low buildings, right? Okay, 15, 20 floors, it's normal. But this is the beach. Right? This is a very soft ground or probably over water. So to fix this, they need to make a very deep piles, and it takes a lot of money. And then the problem is money. But you can see not one building, one whole city ruined because not considering properly the grounds. We have the one we mentioned the other day, the Millennium Building Tower in San Francisco, one of the most expensive, exclusive towers in the world. You have to be a multi-millionaire to have your loft there, right? And those towers has been rotating for months. And the problem is this, the section is very clear. You have a tall tower with a huge slab, right? And piles to help support it. So the piles, you know, if you put a spike on the ground, it gets very strong, right? Just the friction with the ground supports a lot. So the engineers thought just by friction, together with the slab, the building will be supported. And it is, but it turned out to be too flexible. And I think at the day of today, the building already leaned about 60 or 70 centimeters, right? So you can see how it is detaching from the floor. And this is affecting the neighboring buildings. Now they have to make a very expensive plan to re-drill piles to the bedrock under, which would be the initial solution. Why they didn't do it? Well, it's hard to know because it's the news, there's plenty of lawyers. The only people who benefit from this is lawyers, right? For sure. So the question is, they knew making so many piles to the rock was very expensive. So the benefit, the profit would be smaller, right? I don't know why. So when you make a more expensive building, you sell more expensive and people will buy. I don't know, but what's the decision? The developer wanted the San Francisco Port Authority, which is next to it, to pay for the piles. Because they say, okay, that will make safer the building, we will not affect the foundation. But the Port Authority said, that's your problem, right, to do it. And then, since the developer had already some kind of information it could stand without the piles, which is an option, they decided to go without it. And now they have a problem, and they don't know how to solve it, because once they started drilling the pipes, it's still leaning more. So it's very, very problematic. You see, when you try to save money and time at the beginning. So the problem here, greed, is one of the main problems. You could sell at any price and still you wanted to have more profit, right? Then overconfidence of the engineers, telling, okay, it will work, right? And then, yeah, I cannot say because this is very much hidden, but if you look around the news, probably the permit process was kind of obscure, at least. Let's make a contrast, and this is foundation on rock. We commented yesterday. This is Empire State Construction, 1931. Now this is extremely heavy building. And look at the size of the foundation. It's almost solid steel. And it is prefabricated, right? So they brought the construction site, they put in place with much precision. This is quite interesting. Right? It looks very primitive the way they work. It's very weird to see people without a hard helmet, right? But the placement is really precise. by the centimeter, and then the supporting concrete, and this may be 2 by 2 foundation. This is the power of rock, right? And this is why Manhattan was so adequate for high rise, which is not San Francisco Bay, for example, or it's not Gangnam. And the building is almost 90 years old. As I know, there's no issue at all in foundations. And it was done at record speed because those foundations were done in time of days, right? It takes months to make the foundation of those towers. And I brought one more example, just because it is beautiful. Right? I found the photo of the foundation of Eiffel Tower. This could be a piece of architecture or a sculpture on itself. So it's kind of a reminder, beautiful buildings have beautiful structures. Even foundation can be beautiful. Let's go to our black beast. This is where I find more problems. Stress, strain, that ion modulus, that elasticity is nasty. We had one question about the ion modulus, right? It's a bit discouraging, right? Which material has low strength, but relatively stiff? And well, I think the typo was easy to understand, but will not deform before breaking. We'll have a sudden break, right? So stiff means like a break suddenly, right? So it has two things, right? So we know this is not the case with neoprene. And a lot of people replied neoprene, and I think these are the exam-minded people, right? Which remember we spoke neoprene, or it must be neoprene, and they just, you remember some question before and put it without any kind of logic. So this is very wrong. Neoprene can stretch maybe 10 times its length, or maybe less, but so it's not the case. We know that concrete is strong, right? So cannot be adobe brick and aluminum. But we know aluminum is very ductile. So it is stiff, right? But it can stretch a lot before breaking. So it's not the case of sudden break. That leaves us with adobe. And adobe brick is not so strong, fairly strong, but if you stress it, it breaks suddenly, right? It's a fragile brick. So still almost 60% of the class saw it. I would encourage the rest of the class just to take the mystery out of it. So this is just the strength they have and how much they stretch, right? The ability to stretch of the materials. Neoprene, we said, can be as strong as concrete. So it will break about the same tension, but by the time neoprene breaks, it's stretched or compressed a huge lot. One more, this was more painful. We have a thick column in compression. Not this. This is the multi-gesture iPad. So we have it compressed, right? Very thick column. How will it collapse? And we had majority will collapse by shear stress. And of course, columns may break by shear stress, but we're telling of a compressive load, right? Compression will cause only compression. There's no shear there at all. We saw those thick columns in Mexico earthquake when they have side shakes, and then they would break by shear. But it was shear stress, it was not compression, right? We have it's pure compression, the element will break in compression. So this is not the case, right? So it will be compressive failure. This was like really the obvious question, right? Doesn't break in any other way. And then buckling of the column will be with the thin columns, we know, right? We commented. The thinner the element is, the more tendency to have to buckle. Now the silver bars will buckle eventually, but it is after the concrete breaks. So this is not a failure, it happens later, right? So if that column crashes, right, and explodes, the reinforcements will obviously not have support and they will buckle. But the structure didn't break because the steel buckled. First, the concrete breaks, and then the steel cannot hold on itself. Okay. This was meant to be easy. This is overthinking, right? But again, it's to be clear how the logic applies. Of course, pure compression is very rare. This is why when we make laboratory experiments, we have to be very, very precise, because some eccentricity of the load or some kind of a fabrication problem will create actually moments, and the piece could break by shear in some cases. But that's a different matter, right? But in terms of theory, understanding compression. So we have, let's see if the first video works. This is how we do in laboratory the compression test of concrete. You see this protected because the failure is explosive, right? So you have to protect yourself. But see the care, they have to put 2 caps to make sure it's totally horizontal. The load is totally centered, and there's not any distortion on that thing. Let's see if that works. Let me try again. Oh, it should. Now it works.
Well, to the CTTP
I will just try to fast forward.
training videos. ASTM C39 standard.
So it explains how the experiment is made, but I want you to see just how it works. Okay. And it works. So see how careful is the placement, the checks, right? To make sure we have pure compression. And now they are starting to put pressure, and then they check again to make sure it is
Tilt
correct.
the spherically seated block until it is
So
parallel
in
with the top
practice,
of
we
the
have
specimen.
very seldom pure compression. Now it is the
Verify that
experiment
the
going
load
on.
indicator is set to 0.
So it's the first.
Apply up to 10% of the anticipated maximum
I
load
think
to the
people
specimen.
in online can hear the sound, but I think subtitles are okay.
Verify that the cylinder is still centered within the retainers and that the axis of the cylinder does not depart from vertical by more than 0.5 degrees as shown.
Well, I should come forward a bit faster, but. So now
apply the load
experiment.
continuously and without shock at a rate of 35 plus or minus 7 psi
And the load is
per
humongous,
second.
right? This pound, that's
Make no adjustment in the rate of movement during the latter half of the anticipated loading phase.
So you can still, quality is really good, you can
load
still
until
see the cracking.
shows
So you
that
see
the load
vertical
is
cracking and
decreasing
then
and the
sudden
specimen
collapse.
displays a well-defined fracture
This is
pattern.
explosive. And that's the point. It was a huge,
Report the
it's like 50
maximum
tons,
load.
right? To break that little bit of concrete. So that's enough for this.
Note the fracture.
So you see how the vertical cracks appear, but very suddenly it breaks. This is the fragile collapse, right? So if you see the stress strain graph, it is kind of a not totally straight, but suddenly breaks, and then the tension goes down, right? This is why I say that fragile materials are excellent, but they're very tricky. And compression is one of the most dangerous problems we have in structure. By contrast, we have steel, right? And you see the setting is different. This is mimicking double pinned thin steel column. Let me try. No, try again. I don't get the logic of this. Okay, it's working. This is only 1 minute. So here you will see that it's much more easy to predict how things work. So this tensioning, and you see it's already bending a huge tension. But still, there's a point in which the bending goes very fast, and then we consider failure. And well, they show the curve. Let's see, because it's not very long. So like the similar to stress strain diagram. You see it's very straight, and then it bends, right? Is when the buckling starts. So the difference with that kind of buckling failure is that in general, the steel gives you much more room for safety. You have more time to react to it, right? Let's see something in between, timber column, which I found that I think is interesting also. Let me try. Really, I don't know how it works. Now it works. Okay. Oh, thanks to Professor Malaga.
This video shows a standard test on a timber specimen.
You see, this is
parallel
fine
to the
softwood.
grade.
It has
This type of
imperfection,
test is
but
a standard
the
European
breaking point
test for
is
the
clearly not
characterization of
the
timber.
notes.
The specimen is made of
This
glulam
glulam.
GL28.
Makes it
The loading
safer.
diagram
Well,
shows a compressive force evenly applied to both
I'm
ends
afraid
the
of
specimen.
touching here and the video disappearing. This is why I don't go faster.
Compressing forces are now being applied to the specimen. When wood is stressed in compression parallel to grain, each wood fiber acts as an individual hollow column with some support from the neighboring
So you
fibers.
see the very clear
At failure, a number
horizontal
of fibers
slits.
buckle simultaneously,
And in this
producing a
case,
local
we have a bit
reduction
more
of
time.
strength
So from the
leading
initial
to a
cracks
ductile
to the
failure.
failure, there's a bit more time. But those compression failures are
Now,
usually very
if we
tricky. So
slow
you
down the
see, we have
footage,
some
we
kind
can
of
see
a
the
warning,
individual
right?
fibers starting to separate.
This is the point
and
of
buckle
evacuating
under the
emergency. I'm not
compressive
trying
action
anything else
forces.
because just a few seconds later, this is
Besides
slow
lace
motion.
deformation grows as more
The
vertical
element
displacements
collapses,
are
right?
accumulated in
So
the
compression
specimen.
collapse is really, really very fast. And this is not as explosive as concrete. And this is the graph how it
The
works,
graph
right?
shows an initial
Curiously,
linear
this is
force
pretty
displacement
straight. That means
relationship,
that
a
glulam
point in
behaves
which
much more
fiber
like
buckling
perfect elastic
occurs
material.
at around 375
So, and this,
kilonewtons.
I think some of you were asking, so the banana is that concrete, that timber element, right? Sorry, the squash, right? It explodes. And usually it's in thick or reasonably sized elements. When they are very slim, we have the banana, the buckling. We saw enough examples just to have at least in the mind and see how dangerous is this case, how annoying is the other. Both are catastrophic, but again, with fragile materials, timber columns, concrete columns, you have to be very, very careful. Okay. This is one example I like to show in construction materials because it affects also materials class, but I will remember it, right? This is the slide. So collapsing in compression of fragile material is explosive. And there was a construction in 1970. When I said, I entered university in 1979, right? Chelsea Union same, right? So that was very recent. And the architect was one of the professors of the school. Actually, the guy who wrote the methods of concrete structures calculation and design. So he was an expert. And he saw some vertical cracks. And he said, okay, let's reinforce, support, and then we can continue working while we reinforce them. The problem is that the collapse was sudden, right? And 15 people died before they could even do anything. So the architect was condemned to jail. The judge said, okay, you did something to prevent, but you're the most expert in the world. You should have known that was too dangerous, right? He went to jail. He admitted the responsibility and he just died out of grief, right? In the end, investigation showed that the ultimate reason of the collapse, apart from some change in the construction, in the structure during the construction, which is always tricky, the cement company, again, was trying to get more profit by adding more lime than established. And that made the concrete to take the strength, but take much longer. And then the building did not have strength enough. But the architect already died of grief, right? So it's very sad to tell it. So what were the problems? Underestimating the cracks, right? Especially by an expert. Overconfidence of the architect, right? Being expert sometimes is not a good thing. Change during the construction. So when changing the construction are always very tricky because you make a project and you think about it, you develop it, you discuss, you take the best solution with time. During the construction, things come fast. What if we move this column and whatever? Okay, we can do it. And then that's a very good way to get trouble later. And then, of course, greed. We have one common point. Greed kills what less you expect. And I didn't know where to put it but it was quite sad. This is I think, Shiminapatsu here in Seoul. And it collapsed as soon as people started using it. And it's sad because it's like a really, I don't know, thinking poor people have nothing, so let's make buildings with less load ability. So we save money and they can live there. But actually, poor people are the guys who never threw anything out, right? And that's a safety thing. I don't know how much money is saved in reality, but this is one of the most sad failures I have ever seen. Okay, let's go to something which is more familiar, the bending collapse, right? So just a plain beam. So here you will understand very well because this is what we see every day. Let me see, because I have to make this work and put some fast forward. No, let me try again. Okay, it's working. So it's quite long. I will try to
In this
go
video, we'll look
faster.
into the typical flexural tension.
Okay, let's start there. So see how always in laboratory you have like
You can
two
also see a large deflection.
concentrated loads more or
happening
less
in the beam.
thirds of the structure. But this is
The cracks
very,
are widening, and
so
finally the
concrete
concrete
cannot
crosses in compression, and that's where the beam
tension,
fails.
and then it splits both
This is
in
a
compression. So
typical
actually the failure is
flexural
mostly
tension
the
failure
compression
mode
of the
where
top part,
the
but you
tension
see
state
the lower
yields
part
before
is
the
so
concrete
stretched that
crosses, and also
the
it is
steel is always
characterized
all
by
overstretching,
large
right?
vertical cracks and
So
a
this is
large deflection
a
as well.
beautiful
If we look
collapse
into
of
the
a
moment
beam.
versus
So you can see
mid-span
it
deflection
has a
beam,
long period
we
of
see a very
stretching
ductile
and
behavior.
breaking. So this is quite
Initially, the beam behaves
a
linearly.
safe element.
At
Here, the
this point,
steel is doing most
the
of the work,
concrete in tension
right?
cracks,
So
and
we
that's where
have
the
a lot of
beam
time
will
to
start
react
to
and to
behave
repair.
non-linearly.
I don't
And
explain because
at
I
the
know this is
moment
the
of
ones you are
around
more comfortable with. Let's see what happens with a pre-stressed. You saw the collapse of that normal beam. Let's see how one of those collapse. Well, the photo says a lot. Here we are lucky we don't have sound because this is really noisy background music. So they did many trials, but you can see pre-stress being really strong. It's very hard to break. But the collapse is really explosive, right? You can see slow motion. So this is what we're asking. See how we put always like two concentrated loads there, right? Well, the clip goes with the different kinds of stress and so on, but the conclusion is the same. Pre-stressed is very strong, right? But once it breaks, it's totally different than the usual beam. It is explosive. So we have to be careful also in those cases, right? So the point is the cracks, right? And when we have those pre-stressed constructions, they are really, really tricky. We have a bridge collapse in Florida International University, 2018. And again, choosing the construction, the workers saw cracks. The engineers look at them and said, that's normal, no problem. And it collapsed the following day. So this was the render. Very cool bridge with the irregular elements, mixing tension cables, compression columns, slabs. Very complex in a sense, but very elegant and very high technology. The problem, it collapsed suddenly over the traffic, right? This is famous. And the problem was, well, those cracks were serious, right? And it happened when we were starting to put tension to the members, right? So this kind of very irregular structure, you have to be very careful to have things working as you preview them, right? Any small mistake change may make a great difference in how it works. And then the pity is it collapsed because they were so confident of their design that they thought it would be very okay to do it. So they didn't close the circulation under. So this is, again, you can see during the construction, you can see the post-tension elements prepared. This is the provisional supports. And you can see compression elements, tension in different directions, quite elegant, but this kind of a structure in which you rely on a computer model, right? Nobody had done this kind of structure before, so it's totally 100% experimental. Just the best engineers in Florida. But okay, when you never did one thing before, and you know you have so many risks, because we know already, well, at least I hope today we know how tricky is concrete and how tricky is the pre-stressed concrete. With just very simple loads. Here the loads are really hard to figure intuitively, right? Then you have this kind of collapse. So what is the problem here? Again, understanding the cracks, right? And this is experts. Overconfidence on the computer, right? Especially an untested solution on an open area, right? That's really a danger. You're taking a huge risk. And then arrogance of engineers. We calculated, it's safe, no problem. I think this is the only time I put arrogance of engineers, but in the previous case, I put overconfidence. Maybe we can say the same. So let's go to the compressive collapse of an over-reinforced column, right? So we have too much steel on the positive side. What happens? In that case, it will be the compressed concrete which will break. So this is very similar to the column collapse. Let's see if we see it. Okay, let me take this out. And okay, we cannot see it. I could go to the navigator, but then I have to change the screen share. Okay, so you can think, I can tell you. So once the beam starts bending, even though the steel is really relaxed, it never reaches the tension, the concrete collapses, right? And it is again explosive. So that's a problem because you think maybe you put more steel than you need and it'll be safer, and it's not, because we're bringing it to a fragile fracture. So this is something tricky. We have to be careful. Sometimes, when to over reinforce, right? Well, there is one moment when you try to save height, as in flat slabs, and you have over deflection. I hope you can read. One thing we can do to avoid is to increase the height. If we cannot avoid it, is to increase strength, right? Or stiffness. In concrete, will be like adding more steel, right? If we put more steel than necessary, it will have less tension. It will just stretch less. So in that case, we can do, but in that case, when we over reinforce, we have to balance top and bottom to have this balance, right? And to make sure the steel will work at maybe 50%, 20% of the maximum, so it will never stretch as much, and then you reduce the deflection. That's a very common solution, over reinforcing to fight over deflection in slim elements, right? You put more steel stretches less than concrete. But then you have to balance compression and tension elements. Pity of the video. And then I have the first question for you. First question, go to the activity. Those online also, please. The guy of the video, we don't say, was kind enough to show us the reinforcement, right? And the question is, well, we know it has like 2 concentrated loads and 2 reactions, right? And then why do you have stirrups only in those sides, right? Why there's not stirrups in the center? And then can you make the shear and the moment graph of this? We know that for a continuous load, right, shear would be something like this, symmetrical, of course, and moment will be like this. But this is not the case here, right? Can you figure without numbers, just figure out in 1 minute those graphs by what we know. We saw in class only one load in the center, right? Now we have two. So that load divides in two. So certainly not very different, right? So certainly something in between this and this, right? And share should be something between this, right? And this, right? Something in between. But think about it. This is pure logic. And this is probably high school mathematics, but still the easy ones. You may think in terms of integers and derivatives, or just the physical meaning or intuitions, many ways to approach it. But the graphic is very clear. Try, give it a try, whatever. I promise not to laugh, at least not in public. And to tell you the truth, I would panic with this problem when I was 30 years. So then you understand how things work, and then it becomes easy to understand. But I wish you can do it. And I will not tell today. Or should I? Hey, you have to think. You know, I always delay the solution, because if you get the solution right away, you don't try to make the effort to analyze it and solve by yourself. So more than the solution is the process of yourself approaching the problem. Solution is not important. So this is laboratory case. You will never calculate it, right? Or most of you will never calculate it. Okay, 1 minute passed. Put whatever. We have to continue. Yeah, time over. Just, you can keep thinking. It's nice to discuss. So this is a white slide for me to write. So what happened in that compressive beam failure, the one we said over reinforced? So if we make again, maybe the last time we see the Young modulus graph. So we have stress, we have strain, right? If we put steel here, steel will be like something very steep, right? And suddenly yield, and then have a long plastic. Okay, so this is steel, right? So this is the rebar, right? Concrete. How we put concrete in this graph? Concrete stiffness, this kind of a angle is like a 1/10, more or less 1/10 of steel. But the strength is more or less 1/10, 1/20. So let's go to 1/10. It's about here. So steel, concrete will be yielding here. 1/10 will be, probably this is concrete. If you put in the same scale, right? And concrete will break here. Concrete stress strain graph will be so small here, because here will be in the order probably in the 400 megapascal, right? Of concrete will be probably in the order of 20 to 40 megapascal, right? 1/10. And it's much, so the angle would be like a, and so this tells you how we put so much area of concrete and so little area of steel, right? Because steel needs less area. Let's expand this part only to work better. So we have steel comfortably going up, and concrete, it's very hard, but let's say breaks around there, right? So this is again stress, this is strain. Let's have the member of the beam or the column compressed, right? And we have I will not draw the concrete, you know, this is all solid concrete. We have the steel here, right? The rebar. What happens when you compress? It shortens, right? You knew. So with this stress 1, it shortens this little bit, right? And both steel and concrete shorten the same period. So they have to shorten exactly the same because they move together. And at this point, concrete is working at one tension and concrete is working at much higher tension, right? So actually, I would say there's no tension 1, this is F1, right? So F1 will make this kind of shortening, right? The concrete will be working at smaller tension than the steel, because we're in this point. But they move together, they have the same deformation. We put stronger, F2, and then it shortens further, right? And we go to the limit. So if we go to the limit of the concrete, so if we have here, this is, let's see, steel 1, concrete 1, this is concrete 2, right? If this is the limit, concrete will break in this point, but still steel is so happy, right? Still almost does not feel about it. But now the concrete broke. So in this point, concrete starts to crack and starts to swell, and we have that squash collapse, right? So this is just visualization. Sorry, the steel will have this tension, right? Steel 2, concrete 2. So the steel has still room to go much higher, but it cannot. This is why when we use reinforced concrete in compression, we never calculate the compressive stress of the steel to the maximum because it's impossible, right? And this is why the columns break, the concrete explodes, but still the steel is healthy, just buckles because there's no support, right? So just visualizing how they deform together, knowing the graph, you see that the performance is different, right? It's not intuitive, but I think by watching the graph, probably it's easier to understand. They deform together, and the same deformation produces higher stress in the steel than it produces in the concrete, right? And this is deforming together. This is basic elasticity. So any kind of composite structure can be fiberglass with a resin or whatever. We always have to see how they compatibilize the deformation, how they deform together, and what's the limit of their movement. And this is why those the concrete explodes before steel is even having any kind of stress, right? How are we on time? Probably we're halfway, so probably our last black beast. So you know, compression is the most intuitive easiest, but this has some complexity we have to be aware of. Shear stress. Why is it so difficult? Well, probably because we don't insist in the beginning, but when you have bending, moment and shear go together, right? When you have a moment, you have shear stress, right? And we know that any stress has tension and compression, but that's another thing. So this is another experiment. Let's see if I can go to it. Wow, that's beautiful photo. Okay, it's working. This is short, but this will explain. This is in purpose one beam without the steel ropes, right? So you will see that they have the same setup.
Shows a reinforced
Here we
concrete
can see
beam
visually how the
containing no
tension is
shear
applied.
links being tested in bending.
And the left side has no
The specimen is
steel
made
ropes
from
in the map,
concrete
right?
containing
So they in
regular
purpose remove
Portland
them
cement.
to have it
The
a fragile
rebar
collapse.
is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point
You say
bending.
more or less what I told you in better English.
The testing rig is now starting to
So you
apply
see
vertical
already
loads to
it
the
is getting
specimen,
loaded.
and the beam
You will see
starts to
the
deflect.
beam bending.
Then
Actually,
quite
this is a
suddenly,
beam which
we
should
have an
break
explosive
by
failure
bending, not
near
by
a support.
shear. But again, explosive,
This is what we call a shear failure, and it is
fragile crack, right, by tension, and it's more or less 45 degrees. This is why the best way of reinforcing is having the reverse crossing. Nowadays, it's very complicated, so this is why you put steel ropes, right? So the steel ropes will absorb, but they have to work together with the longitudinal steel, right? Longitudinal alone will do nothing. Steel ropes will help. They work together. That's another thing about how we modelize it. But this is shear stress. And why? Because this is where the tension happens, right? Remember, this is this kind of, in this part, we are deforming like this, right? We're skewing in that way. So that means the tension is applied in this area, so the crack will appear in this diagonal. Just that. This is what's in class. And there's something sometimes, so in shear, we consider not stretching or shortening, but just the angle, yeah, the rotation. But this image is very clear to see what's happening here. And sometimes students copy in a very strange way. So when you copy, at least copy after you understand the idea or ask, because this is just confusing, right? There's no, so the arrows do not follow the image, so it's very difficult. There's a visual understanding of what happens here. So careful when copying, right? And you will see not only on class notes, on assignments, often what you find in internet, if you're not careful with where you find the information, many bloggers also copy things, they paste, they comment, and then they copy the wrong thing or in the wrong place. So you have to be very careful with those bits of information. And this is something what happens in reality. What happens, we have a longitudinal steel, we have still stirrups, but there's not enough. And the same what happened with the beam, there is a moment in which steel is not enough and the concrete itself will collapse, right? So stirrups will work to a degree. Over reinforcing with the stirrups will not make you safe against any kind of tension. But again, this is very clear fracture. So we had this kind of activity in class, right? In which we said, how would be the punching of a two-dimensional slab? This is exactly the same in 3 dimensions. Calculating is a bit more challenging, but because of practice and theory, we know that it happens like around the column. So usually we consider the punching fracture happens at about the depth of the slab, more or less, or half the depth. It depends on the codes, right? It's the most critical area because it doesn't happen next to the column, it happens a bit behind. You see the previous photo, right? Very seldom it happens because the concrete column is a full solid, so this area is really stiff. So it happens a little bit beyond, right? It is hard to modelize, but to be practical, let's shorten this. Okay. So to modelize, we consider just one area around that column, right? So it's actually the same put in 3 dimensions. So how would we improve the conditions for this shear? So most people were correct in slightly the slab thickness with the capitals because we saw in class 60%. So okay, we put capital out, have more concrete, so that area is reinforced, right? So we have in section, we have the column, and if we add more concrete here, this weak area is already reinforced, so the stress is diminished. So this is correct. This is something that half the class thought would be correct. So we can, instead of that, we can add steel columns, right? Like, or steel frames, it's like Empire State Foundation, right? So also steel is much stronger in shear. Rebars have very little area, but still may have enough area to compensate for that over stress. You have to calculate it. So this is a possible thing. The stirrups, yeah, half the class thought about that, and it's perfectly okay. So we can put stirrups in this area, right? So vertical bars will always help. How does it work in 3 dimensions? So you will have the typical top and bottom bars, right? Let's say the bottom bars are in blue below, and then you put the stirrups just in top and bottom, the same as you do in beams. The effect is the same, right? You can also have the bend bars, so you can use also this kind of bars, right? And you will see it often around the slabs, because slabs are expensive and you can spend more time doing that. So stirrups are okay. And very few people thought, but if we make the larger the column, right? If we have that column with the slab around, and we make the column larger, we increase the area of fracture. So that stress is shared in a larger area. So sometimes just increasing the stress of the columns is enough. It's very intuitive, right? If you have a problem of punching, the thinner the column, the easier to punch. This is we know by experience. So if you put a thicker column, it's more difficult to punch. How do you punch things? By having sharp edges, right? So it's very easy way of doing. The others do not work. Total depth is a possibility, but the condition was not making it heavier, right? So this is okay, but the condition here was not making the structure heavier, right? So that will not help. Longitudinal and reverse by themselves will not help, right? They will help in conjunction with the stirrups. This was how I explained in 2017, but it's more or less the same, right? The fracture area is around the column, right? So you can increase the thickness, you can increase the column, you can add the capital, or you can add the stirrups. These are the 4 options we have recommended. And then the steel, of course, you have a stronger material and it will work also. And then we go to one of our favorite collapses. I have to make sure we finish. I don't want to run, but I don't want to go too slow. This is a famous Surfside collapse in Florida. Investigation is ongoing, but there's plenty of documentation. So for what I read, I saw, and I think it was both shear stress failure, which brought then a buckling of the columns, right? And the result was catastrophic. So it's really embarrassing because, again, Florida is supposed to be one of the safest states in the United States because they have the hurricanes next to the sea. The codes are very strict, and the permit process is very strict. But again, money is money. If we see the photos of the collapse, something strange, and actually something all experts saw immediately, the eyes went through, right? This is where the parking slab was. So the parking slab just fell down, pushed the cars down. So all those cars were in this plane. You see the columns are clean. In a typical shear fracture, columns would have some kind of remaining of that kind of solid element of concrete, right? And you will have a lot of steel because this is like a really, you can see it's really thin slab. So that means to have, they have not capitals, of course, but probably reinforcement of steel, stirrups, something there. There's almost no steel, like it, just 2 lonely bars around. That's very strange, very weird. So this is clearly punching, but really over punching, right? How come it is like so well? We don't know very well, but the case is very thin slab, just for punching, and probably reinforcement was insufficient, and it went down, right? So this might be the initial stage of the collapse. But then why the column buckling? Well, the moment you lose the slab, the columns become higher, right? So the proportion changes, and then buckling becomes one issue. So the diagram of it, and actually it happened more or less in the middle of the building. So it's quite high-rise building with one basement. You have the columns, right? And some area in the central part collapsed, went down. That made those columns in the center to be very slim. And then, since they have a huge load on top of it, those columns just buckled. And it took several hours, actually. People were hearing cracking and things, but when you hear a building cracking, just leave, just in case, right? And then maybe it's not necessary, it was not great. Building scrap because many other things, right? But concrete, reinforced concrete building cracking is very suspicious, right? If you hear noises in a reinforced concrete building, which you didn't hear before, and vibrations, because people were feeling like it was not wind and so on. So the central part collapsed, and then it brought all the rest. It pulled the rest of the building down, right? This was there's more than that. But the question is, from the beginning, they said the pool was loosened, so the rebars were oxidized. They were already having many cracks. The condominium owner said, okay, let's have it's a lot of money. Let's wait for next year. Let's have a more report. Let's call the whoever. In that time, the disaster came, right? And this building, because it was warning for years, right? The collapse was sudden, but it has some kind of advice. You will see many things in YouTube about this. And one of the things they will say, okay, the slab collapsed because of punching. This is very clear. If they had beams, right? So if the connection of the column and the slab, let's say the slab in that section had a beam, right, next to the column, that beam, as we do here, would have area enough to support the shear. Yes. One beam would have made it safe. And this is why you have beams everywhere in Korea, because after Samsung department store, engineers have panic of the slabs and they put beams everywhere. So this is yes. But we saw already 4 or 5 possible ways to solve it, right, without those beams. So telling, you have to put beams everywhere. Okay, the problem is not the slab, the problem is a badly designed slab. Of course, there were changes. Some columns disappeared, some beams disappeared during the construction because they were not convenient. They added 1 or 2 floors. So it's very strange things going on under the carpet with the developer and the city and so on, right? Which also may have influenced. So conclusion about this, apart from the clear loss of lives, it's like a most complete greed, obviously, right? They increase the height and they saved in materials. They have very cheap engineer apparently, Roberto was not very good engineer, careful with engineers. Actually, he was already prosecuted in several states and he just went to, he had very strange connections with the developers. The developers have strange connections with the, this dark power. Changes in the project. They added 1 or 2 floor plans, they suppress beams. That also affects the whole stability, right? Obscure permit process. When things happen in the shade, things are very hard. And of course, poor maintenance, stingy owners, right? That happens a lot with the condominiums, right? Nobody wants to spend money and say, okay, there's some kind of responsible, let's get somebody to do it for us, or let's wait. If you have a car accident, for example, or some car hits you, you go to the hospital, you get healed, and then you pass the bill to whoever was responsible, right? With buildings, it's the same. You will not wait on the road, losing your blood and dying, waiting for the church to say, okay, you pay the hospital of this guy. Doesn't make sense. But in buildings, that happens. So the owners, I think they have a lot of responsibility here also. Well, this is quite sad, at least. And then I don't know where to put it. I have the rest of the watch. 10 minutes. What happened with iPark? I cannot say because most reports are in Korean. Actually, it's very hard to find any information in the news anywhere else. But I can see, apparently greed happens there. It was a Hyundai, no greed. Okay, I will not discuss it. And then pressure in subcontractors. And this is what problem of management. This Hyundai, subcontractors, sub, and they all push down as much as they can. It's like the power for fast and cheap. And that has consequences. Sometimes you don't see it, sometimes you see it, right? Incompetence of the managers, right? Which is related to that. So that multi-layering in which you just rely your responsibility on somebody else and you just don't want to take any blame about it, right? I don't see the president of Hyundai taking much responsibility about this, but probably I'm wrong. Changes in the project, that was clear. It's always tricky to change things in these projects, as I said. And then basic science. Maybe I don't see so much in materials because it is so obvious, but in most of the world, never pour concrete under 4 centigrades, and never when it is freezing. It was snowing there. Concrete is water-based, right? If water freezes, the whole chemistry goes on. You may have additives in the concrete, and we said, but those additives change the properties of the concrete. May need much more time to harden. And I have this once in Spain. So it happens very seldom, but they put the concrete and that night it froze, right? we went to see it. We demolished the whole floor. Actually, it's very easy to demolish because it's very soft yet, right? So it's the easy way of doing, but there's no way to keep it, right? So you can do it. You can, for if it is worth, right? Just to save. Yeah, okay. If you save a few weeks, it's more money you get, right, in the promotion. But wow, does Hyundai need much more money? Maybe no, they need a lot of money, right? But greed, right, and the basic science, right. And there were more things. I will not go into it, but it's really sad, right? When we saw the news of the collapse, we saw pouring concrete under the snow. Almost was saying, what are they doing, right? What they are doing? That week between floors does not make any sense in that time. Might take 1 month or 2. In Finland, I don't know now, but I was involved far in a construction in Finland maybe 30 years ago. So not myself, my friends. So once we pass the threshold of October, all concrete construction stops until May. Full stop, right? You can do inside work, you can do steel work, but you will not do anything dealing with water. Beams and columns. So, okay, the stress, this question was mostly well understood. Again, shear stress was a bit worse, but I think these basic formulas were okay, right? The cellular beams was a bit more surprising. We're telling, okay, I put alveolar, that Spanish went on. We call it alveolar in Spanish. Cellular beam, but castellated, right? This kind of beam, we said, they make sense to have a wood performance against moment, against the deflections, but it has very little material, so by shear is kind of weak. So we have in large spans, but medium large spans, but not heavy loads. It's just logic, right? It's in lecture, so I don't see. And there was one interesting question about you. Why do you make the holes hexagonal or circular, not triangular or random, right? Well, you can do, but first it's fabrication. Hexagonal is the most rational. And then once you have those elements, you have a tension concentration in those points, right? So you put triangles, you have very, very concentrated tensions in those peaks. And we try to avoid it always in the structures. This is why I always say, and with rounded connection and so on. This one, how the steel affects the reinforcement. And I think we have to go short some things. So in this case, the moment is rigid with the column. So the connection is rigid. So the column will get some of the moment, but we'll have quite reasonable positive and negative, and some of the moment will go to the columns, right? So the columns will help here. In this case, when the beam starts to rotate, it will crack here, no matter how solid. So it will be mostly supported by the steel, and it will act like a real hinge, right? So here, the moment will be almost perfectly like a hinged, and near hinged because when the load is small, still you will have some, so with very small loads, in this case, you will have still negative moment because the concrete can stretch a little bit, but the moment you increase, this will break, right? And then it will just go down as you increase the load. And this is something we can use in design. So we can fine tune the negative rebars to have this negative moment as much as we think it's possible, right? So we don't affect too much the columns. Of course, if we have a very thick column and very thin beam, very well reinforced, here this really like a really almost the full rigid connection, right? But if at the opposite, you have very thick beam with very thin column, even though we put as much negative rebars as we want, this column will bend. So in reality, it will be almost like a hinge, right? So the relative rigidity of those elements will have as much to do as it has the way we use the rebars. And then some people said, okay, what is the point of having the steel? Like we said, if we totally weld and put reinforcements, this is rigid connection. We said, if we weld only the the core, right, this is almost hinged. Why? Well, it's really not a hinge. But if you see the section of the I-beam, right, and you see the section only of the web, right, this can support a much, much bigger moment than this other one. Maybe like 10 times or probably 20 times than only the core. So that means that in this case of the beam, the full moment will be like this, right? In this case, with the full connection, if you have this, that negative moment will be probably almost insignificant, right? So it's almost a hinge. And that 10%, 5% will be perfectly embodied in those safety margins, which we said is like a 40 to 60% always. So we don't worry about it so much, okay? Some people asked about the notation, we commented already. So moments are often said positive up, but I see more intuitive, and this is taken from an American handbook, to put the moments positive down, just because it connects to the deformation. So if we know the structure deforms in this way, right, we know the moments will be in this area. So it's very easy to see the moment relation with the deflection. And this is why I think it's more intuitive, and I follow this kind of convention. This I reserved just to comment what we said. High rise was quite okay. The only part which was a bit more controversial was 100 floors, can be assembled tools, can be ramen, right? But what we said, the tripod system is by now the one which has the highest record on height, right? So it's just to go back to the lecture and see what we're commenting there. And then the grid, everybody understood, so we don't need to explain it. This diagram, actually this is a simplification, right? If the load is in the beam, maybe 20% of the load will go to the sides, and maybe just 5% will go there. So there's a small, in reality, there's a small share of that stress in the ramen, but most of the load will be in the center. It's kind of irregular. The grid goes smoothly and will go to the sides. So any load anywhere is instantly shared by the whole building. Ramen is much more concentrated. This is why diagonal structures are so safe and so intuitive. And 60 degrees is also the angle in which we consider a load dissipates in a solid brick or concrete wall, right? So if you put a load in a solid wall, we consider the tension will move in about 60 degrees. So the 60 degrees diagram is quite easy to draw, is easy to detail, all elements are equal and so on. And it has some kind of physical meaning. Long span, because our dear Pratt and Hall, and again, this is a terrible diagram, but the point here is that having the diagonals in tension will save always material. Some people said, okay, you can remove those elements, but also you can do in the Pratt. You can also put the supports there, right? So it's about saving material and visualizing how things deform. There's not more. And again, please, because it still is not weak against compression, right? Last time I said, right? And we have the problem of that spaghetti. It is just the element, which is too slim and it buckles, right? We see the structural steel is the same in tension and compression, exactly the same, no difference. Some people asked about the folding structures, right? Well, you fold paper very easily, but how do you fold concrete or steel? Of course, you fabricate it in that shape. You don't make it flat and then fold it, right? Strange question, but very small scale still you can fold, but full structures you will make full pieces and then you will weld them, right? Whichever shape you want to make, right? So we call them folded because of the shape, but doesn't mean we fold them physically. That's the result. And then we're almost on the end. The long spans. Do you mind just 2 more minutes? I promise to finish on time. It's just 5 or 6 slides left. So this is very well understood, right? The long spans problems. And I bring Spain. This was almost 10 years ago. The bullfight ring, and it was covered actually by the best long span company in Europe, which is in France, with the best construction company. So they were top. but it collapsed, fortunately, before using it. It was when they were still checking how it worked. Fortunately, they did. Why? Well, you can see that those structures, always it is the compression bars which fail by buckling. This is the most common case, right? Sometimes the tension cables will break, and that also creates a collapse, but most cases are this kind of compression. And why? Well, overconfidence, again, of the engineers, and then underestimating, because in Madrid, you have sometimes wind and a lot of heat, right? Asymmetrical heat. And usually we consider heat load and then wind load. And this is my fight with engineers. What happens if we have wind and earthquake together? It is very rare, well, but can happen, right? So here, maybe it was the case. And then it has not been covered. We didn't recover from that. Another case, 1978, Hartford Arena. It was, again, changed during the construction and computer case. So the details were perfectly aligned connections. It's just a dimension more complex. It is very difficult to make, so they just move a little bit the connections to have possibility to do well. This makes much weaker connection. And then you have those eccentricities in this area, right? Which you don't preview. And then the whole arena collapsed. Fortunately, without casualties. So again, there's no redundancy. It was thinking the computer solved everything, but they didn't check the construction really matched the computer hypothesis. Overlooking of buckling, right? And fatal changes in details, again, changes, right? So it is almost the last question. Let's spend 1 minute to it. Try to remember common causes of failure. And I promise this is the last question today, and then we can go home after 1 more minute. This is just a basic exercise of memory. Many of the problems are repeated, right? And are very common. So how many can you remember? The common causes of collapses, right?